Okay, so thanks for sticking around until the last talk of the day. So this is joint work with my advisor Aditya, who's also here at PLDI. So the code snippet here shows how to fetch a response from a URL and copy it to a buffer and return the contents of the buffer as a byte array. Okay. So the problem with this is that this get response function here blocks until the network is ready with the result. Okay, so these synchronous or blocking calls are bad because they block and reveal latency to the user, and they tie up resources like calling threads. During this time, this particular thread cannot do anything else. Okay. Uh, so because of this, the asynchronous programming paradigm is gaining in popularity. In fact, most modern languages make it easy to write asynchronous code using the high-level async await primitives. So let us see what these are. This is the asynchronous counterpart of the method shown earlier. So first pay attention to these keywords: async, which is used to qualify a method as asynchronous, and await, whose semantics we'll see shortly. The task type here, returned by asynchronous procedures, is central to asynchrony in C#. So task objects are stateful. They begin in an incomplete state when the asynchronous procedure is in flight, and they are marked as complete when the procedure completes. And task.result is the unwrapping operation, which actually produces the value uh, returned by the asynchronous procedure, provided the task is complete. Otherwise, task.result or task.wait block. Okay. So now let us understand what the meaning of this await is with a dynamic run that begins at method entry. So when this method is called, the initial sequence of statements is executed uh, until this call to get response async. Now get response async is itself an asynchronous method, which means that it will not block at this point. Okay. Instead, it returns a task object w task that get contents async awaits. Okay, the semantics of the await are as follows: if w task is incomplete, get contents async returns a fresh incomplete task to its caller along with control. Okay. Now get response async will eventually complete when the network data is available. At this point, it will schedule the subsequent part in this method shown by this red box here as a continuation. Okay, the continuation eventually runs until the subsequent await where something similar happens, and finally the contents are available as this byte array, and we return to our caller. So the task returned by get contents async to its caller is only marked complete at this point using the task set result signaling method. This does not appear in the code because it is compiler generated. Okay, so with this background, note that there is also a possibility of sequential flow at the await in case the awaited task is already complete. Okay, so with this background, we are ready to look at an example of how deadlocks can arise in this model. So this is our running example that we saw earlier. What we have here is a client of get contents async called sum page sizes. What this does is it iterates over a list of URLs, fetches the contents from them, and sums the sizes of the byte array. That part of the code is not shown because it's not important to us. So let us understand how this behaves. When sum page sizes is invoked, control flows until this get contents async, and as before, uh, we call get response async at this point and get a task in return. Uh, in the case that this task is incomplete, recall that control returns to the caller, which in this case is sum page sizes, and the next statement is executed, which is task.wait. Okay, at this point get contents async is incomplete, so this is a blocking call and it blocks the thread t. Okay, now eventually get response async will complete as we saw earlier and schedule this continuation onto t. Will this continuation get a chance to run? At this point, recall that T is in a blocked state. Now, who's going to unblock T? T will be unblocked only when uh, we actually return from get contents async. Okay, so what we see here is a thread T that's blocked by a wait. The wait has a corresponding set result here, and the set result will only run if some continuation gets to run on the same T. Okay, so this leads to a deadlock cycle, which has so the crux of the problem is that the incorrect use of a blocking operation together with an asynchronous operation like get contents async has led to a deadlock. And an interesting feature of this deadlock is that it is present even in the absence of explicit thread creation and locking. And in this particular example, it has occurred even with just one thread. Okay, so our goal in this work is to detect these deadlocks. In fact, we propose the first deadlock detection technique for async await based C# programs. Async await is a feature that has already come or is coming to all these other languages. And in fact, all major web browsers support async await based JavaScript programs. So we are hopeful that our algorithms will apply to a broad class of systems. So the way we solve this problem is to introduce a new program representation that I'll tell you about, the continuation scheduling graph. So unlike call graphs that model only synchronous control flow, we also model both synchronous and asynchronous control flow in addition to some scheduling information as to where continuations might get scheduled. And finally, we implement our algorithm in a tool for static deadlock detection. The tool is quite effective in practice, finding 43 new deadlocks in C# libraries, 40 of which were fixed by the developers. Okay, so the challenges here are that asynchronous programs are a maze of synchronous and asynchronous operations, and in general, it's not trivial to get a global view of the underlying scheduling choices. Detecting deadlocks in these programs require reasoning about dependencies, and in order to correctly capture these dependencies, we need to see what the continuations of a method are and who could call them back. This is difficult because procedures could have multiple await statements in loops and branches. We also need to figure out what threads a continuation might run on. Uh, and this is complicated by the fact that C# allows dynamic thread creation and the scheduling of individual continuations is configurable. And finally, we need to infer the correspondence between blocking and signaling procedures on tasks. Tasks are first class objects and can be passed around, which means that you could await a task very far from its creation site. So the first step in our solution approach is to evolve this program representation called the continuation scheduling graph. So as I mentioned earlier, they extend call graphs by capturing asynchronous control flow and scheduling information. So for our example, we start out with nodes that look similar to the nodes in a call graph, except that asynchronous nodes representing asynchronous procedures are expanded out to show all their continuations explicitly. Then we add these synchronous call edges, which are standard. I mean, the semantics are exactly the same as in call graphs. We add these state machine edges, which represent the possibility of sequential control flow within an asynchronous method in the case that an awaited task is already complete. We have these callback edges. So what this says is that when get response async completes, it could schedule the continuation represented by responded for running. And finally, we also have scheduling information. So the annotations next to these nodes are abstractions of threads. So for example, here we know that set result could execute either on the main thread or a thread pool thread. Okay, so this is the program representation. So using this program representation, we construct this, we can run a deadlock detection algorithm on this structure called a DDG or a deadlock detection graph. The nodes here are abstractions of threads, blocking and signaling procedures, and the edges capture dependencies between them. Uh, And a cycle in a DDG is a necessary condition for a deadlock. Going back to our example, uh, first we start with the nodes here are abstractions of threads, blocking and signaling procedures. So first we add this edge because the CSG tells us that the wait could execute on T. We add this edge because the receivers of this wait and this set result may alias. And finally, we add this edge because uh, the execution of set result on T depends on the execution of this continuation on T. And this is known from reachability information in this CSG. Okay, so that is the overview. Now I'll get into a few technical details of how we actually go about CSG construction. The first step is to model asynchronous procedures as state machines so that this await construct goes away. So what here is an example asynchronous procedure M with a sequence of statements S1 and a wait followed by a sequence of statements S2. Okay, so our strategy is going to be to use some syntactic rewrite rules that are inspired by the compiler transformations performed by C# and C++ compilers and so on to rewrite this as a state machine. Okay, so the first step is to uh, uh, rewrite the body of M with code to create the state machine, set its initial state, invoke its transition function synchronously, and finally return a task. Okay, and the state machine looks somewhat like this. So don't try to read the code at once. I'll tell you what it does. So the state variable controls what state the state machine is in, and these cases correspond to various continuations within this M. Okay, to convince ourselves that this is correct, uh, let us look at the case where M is invoked for the first time from some caller. So what happens here is that we set the initial state and jump to this point. Now we go to the case 1 where we jump to this label L1 and it executes S1 as is expected. Now the desugaring of await, if you recall, the semantics of await are that if V is complete, then just proceed to S2. If not, you need to schedule this continuation for execution later. Similarly, here if V is complete, we go to L2, which just executes S2. And in the case that V is not complete at this point, we ask V to schedule M itself on completion. Okay, so uh, so when V actually completes, M will be called, but now the state has been set to 2 earlier, so we'll go to this case and jump to L2, which resumes at this point as per the original semantics. Okay. So now our goal is to go from something like this to this nice thing that we have here in our picture. Okay, so the way we do that is to compute a map from instructions to values of state. For example, all the initial parts of the code should get uh, mapped to this state 1. Okay, and the transitions are determined by assignments to state. Okay, so for example, this S1 is reached with a value of state 1, and this assignment here of 2 to state means that we could transition from state 1 to state 2. Okay, so this is accomplished by a value set analysis on rewritten code for values of the state variable. Some additional information is also recorded on the rewritten procedure. The semantics of scheduling a continuation are as follows. By default, the continuation resumes on the thread that ran the await. For example, the thread that ran the await as part of the initial state of this method would schedule responded on the same thread, okay, unless configured otherwise. So the other languages that are adopting async await are likely to follow the same semantics to avoid illegal cross-thread accesses. In particular, a continuation that is of a method that touches UI objects better run on the UI thread again. Okay, so now that we have these state machines, the next job is to compute these callback edges. So that is determined using the aliasing information between an awaited task and the task that is the receiver of a signaling procedure. So, because when a task is marked as complete, that is when the continuations are scheduled to run. So, in particular, because initial had an await W task and uh, the set result called by get response async was on a receiver that aliases with W task, we add this edge. So what we use an existing points to analysis framework, SEAL, to uh, compute the points to information. So this can handle delegates and higher order functions, which is quite important in our setting. And for our experiments, we configured it to be flow insensitive and fully context sensitive. Uh, Now let me say about how we compute this node to thread mapping that says where a particular node could run. So as a standard, we abstract threads by their start method in the CSG, and we use a single abstract thread to represent all thread pool threads. Synchronous call graph reachability preserves threads. What that means is that if some page sizes is known to execute on an abstract thread T, this synchronous call means that setup URLs could execute on T as well. Next, we use local continuation scheduling constraints to infer global behavior. Okay, so what this means is that if the initial part of get contents async is known to execute on T, by default responded would execute or be scheduled on T as well. And once we know where responded would be scheduled, we would then know where copied would be scheduled and so on. So these local constraints need to be propagated in this graph using reachability information, and we do that using by modeling them as set-based constraints and solving them. Okay, so now I'll talk a little bit about the experimental evaluation. So we built this tool called Deadweight. It's built using the Microsoft Phoenix compiler framework, and as I mentioned earlier, it uses SEAL to obtain call graph and pointer analysis information. Uh, okay, and it models important .NET framework and task parallel library idioms. So in addition to the concurrency introduced by async await, uh, there's also concurrency injected by certain framework methods that it is important to model, and Deadweight does this. Uh, it also incorporates techniques to prune false positives. For example, cycles involving a thread pool thread are not reported because in .NET the thread pool can grow on demand, and we observed that these kind of cycles don't really correspond to real deadlocks in practice. Finally, Deadweight reports deadlock cycles and debug information. The debug information includes abstractions of paths to blocking and signaling procedures, and also a graphical representation of the CSG. So we evaluated it on 11 open source libraries. So 5 of them are from the Microsoft Azure repositories on GitHub. All of them are quite popular with more than 100 stars, and some of them with over 500 stars. So the point here is that they were mature libraries. And the others came from diverse domains, including an accounting software and the Office 365 reporting web service, etc. We manually wrote clients to reach every blocking call in these libraries, and the deadlock analysis took 20 minutes on average for each client. We reported 66 deadlocks in total, of which 43 were real and new, and 40 have been confirmed and fixed by the developers already. The fixed strategies range from significant refactoring of procedures implicated in the deadlocks to removing the blocking APIs altogether. To just show you some screenshots from GitHub now, documenting the developer and user response. So this was a deadlock that I had reported in the Office 365 benchmark, and other users also have spent hours debugging this issue. And in general, the developer response was positive. The lead developer of TweetInv, a Twitter REST client, was quite enthusiastic, and the developer of HBase simply removed all the deadlocking methods that we reported to them, okay, which is kind of a radical fix. Uh, so, in related work, Bierman and his colleagues were the first to give an operational semantics for asynchronous C#. In the supplementary material in this paper, we extend their semantics to explain certain scheduling aspects that they don't cover. Okur and his colleagues preemptively correct common misuses of asynchrony in C#, including a particular syntactic pattern that could lead to deadlock. In contrast, we do a whole program analysis to detect deadlocks. And there's a rich body of literature on deadlock detection for multi-threaded programs, as well as these programs that combine the actor model with object-oriented features. So I'll conclude with this. So the message of this paper is that mixing synchronous constructs with async await can lead to deadlocks. So we propose the first deadlock detection technique for asynchronous C#, and we have introduced these CSGs to model mixed async and sync control flow. We hope that it will serve as a useful representation for other program analysis, such as race detection and so on, of these asynchronous programs. So in future work, this paper we explicitly configured our points to and call graph analysis to be as precise as possible in order to not overwhelm the developer with false positives. But yeah, obviously doing this has an impact on scalability. So we would like to explore other points in this design space, and we want to integrate our work with existing work on multi-threaded deadlock detection. In particular, investigate how locking can interact with asynchrony and so on. So the tool is available at this website. It's open source. So thanks, and I can take questions.
I'll ask a question. So, it seems like you, if I understand correctly, you kind of reduce this. By understanding the semantics, you reduce the problem to a non-model checking problem.
Yeah, yeah.
So, and trying to understand if there are insights that, based on the models you can construct, allow you to do other types of properties from deadlock. So maybe can you check liveness, or can you do any type of model checking using temporal logic or so on. So what was special about that detection?
I guess it was so in general we didn't so we use reachability in a fundamental way, except that it is reachability in this abstract representation of programs. So which is why we are able to sort of over approximate the set of deadlocks that could occur at runtime. So I mean, so I guess you would have to define some appropriate representation and reachability over it for maybe these other properties.
And your model is an over approximation only with respect to reachability, but it's not a similar model. Like it doesn't simulate.
No, because we do lose some information in the sense that it does introduce some over approximations. We lose ordering information in certain cases and so on.
Okay, and there are other questions? Since we have to walk to the other side of the campus, I say we end now. And thank the speaker again.
Thank you.